and others find it kind of dull and difficult. Especially kids, you know, some of them are just eat it up. And I don't know why it is. It's the same perhaps for all subjects. For instance, lots of people love music, and I never could carry a tune. And I lose a great deal of pleasure out of that. And I think people lose a lot of pleasure who find science dull. In the case of science, I think that one of the things that make it very difficult is it takes a lot of imagination. It's very hard to imagine all the crazy things that things really are like. Nothing's really as it seems. We're used to get, you know, hot and cold, and all that hot and cold is the speeds that the atoms are jiggling. If they jiggle more, it corresponds to hotter, and colder is jiggling less. So if you have a bunch of atoms, a cup of coffee or something sitting on a table, and the atoms are jiggling a great deal in the coffee, and they bounce against the cup, and the cup then gets shaking, and the atoms in the cup shake, and they bounce against the saucer, and the heat heats the cup and heats everything else. And hot thing spreads its heat into other things by mere contact, because the atoms that are jiggling a lot in the hot thing shake the ones that are jiggling only a little bit in the cold thing, so that the hot heat, we say, goes into the cold thing. It spreads. But what's spreading is just jiggle and irregular motions, which is easy to kind of understand. It brings up another thing that's kind of curious. That I say that things jiggle, and if you're used to balls bouncing, you know they slow up and stop after a while. But we have to imagine with the atoms a perfect elasticity. They never lose any energy. Every time they bounce, they keep on bouncing all the time. They don't lose anything. They're perpetually moving. And that the things that happen when we say something loses energy, if a ball comes down and bounces, it shakes irregularly some of the atoms in the floor. And then when it comes up again, it leaves some of those atoms moving, the jiggling. So as it bounces, it's passing its extra energies, its extra motions, to little patches on the floor each time it bounces, and loses a little each time until it settles down, we say, as if all the motion has stopped. But what's left is the floor is shaking more than it was before, and the atoms in the ball are shaking more than they were before. That the organized motion of all these atoms moving the same way, falling down, and the quiet floor is now transformed into a ball sitting on the ground, but all that motion is still there in a form, or the energy of motion, in the form of the jiggling of the floor, which is a little bit warmer. Unbelievable. But anybody who's hammered a great deal on something knows that it's true, that if you pound something and hit it a lot, you can feel the temperature difference. It heats up. It heats up simply because you're jiggling it. This picture of atoms is a beautiful one, that you can keep looking at all kinds of things this way. You see a little drop of water, a tiny drop, and the atoms attract each other. They like to be next to each other. They want as many partners as they can get. Now, the guys that are at the surface have only partners on one side here, in the air on the other side, so they're trying to get in. And you can imagine this team of people, these teeming people, all moving very fast, all trying to have as many partners as possible. And the guys at the edge are very unhappy and nervous, and they keep pounding in, trying to get in, and that makes it a tight ball instead of a flat. And that's what, you know, surface tension, the way when you realize, when you see how sometimes a water drop sits like this on a table, then you start to imagine why it sits like that, because everybody's trying to get into the water. And at the same time, while all this is happening, there are these atoms that are leaving the surface, and the water drop is slowly disappearing. I find myself trying to imagine all kinds of things all the time, and I get a kick out of it, just like a runner gets a kick out of sweating. I get a kick out of thinking about these things. I can't stop. I mean, I could talk forever. If you cooled off the water so the jiggling is less and less, and it jiggles slower and slower, then the atoms get stuck in place. They like to be with their friend. There's a force of attraction, and they get packed together. They're not rolling over each other. They're in a nice pattern, like oranges in a crate, in a nice organized pattern, all just jiggling in place, but not having enough motion to get loose of their own place and to break the structure down. And that's what I'm describing as a solid. It's ice. It has a structure. If you held the atoms at one end in a certain position, all the rest are lined up in a position sticking out, and it's solid at the end. Whereas if you heat that harder, then they begin to get loose and roll all over each other, and that's the liquid. And if you heat that still harder, and they bounce harder, then they simply bounce apart from each other, and they're just individual, I say atoms, there's really little groups of atoms, molecules, which come flying and hit. And although they have a tendency to stick, they're moving too fast. Their hands don't grab, so to speak, as they pass, and they fly apart again. And this is the gas we call steam. You can get all kinds of understanding. When I was a kid with this air, which I was always interested in, I noticed that when I pumped up my tires with a bicycle, you can learn a lot by having a bicycle. I'd pump up the tires that the pump would get hot. And that's also understandable. See, as the pump handle comes down and the atoms are coming up against it and bouncing off, and it's moving in, the ones that are coming off have a bigger speed than the ones that are coming in, so that as it comes down, and each time they collide, it speeds them up. And so they're hotter. When you compress the gas, it heats. And when you pull the piston back out, then atoms which are coming fast at the piston feel a receding or sort of a give. It gives, and it comes out with less energy. It's like going up against something which is soft and yielding. It goes boom, boom, and it loses. So as you pull the piston out and the atoms are hit, they lose their speed and they cool off. And gases cool when they expand. And the fun of it is that all these things which you see or notice in the world about it, the pump heats the gas, or the gas cools when it expands, or the steam evaporates until you cover the cover, and all these things you can understand from these simple pictures. And that's kind of a lot of fun to think about. I don't want to take this stuff seriously. I think we should just have fun imagining it and not worry about it. There's no teacher going to ask you questions at the end. Otherwise, it's a horrible subject. The atoms, like each other, to different degrees. Oxygen, for instance, in the air would like to be next to carbon, and if they get in near each other, they snap together. If they're not too close, though, they repel and they go apart, so they don't know that they could snap together. It's just as if you had a ball that was trying to climb a hill and there was a hole it could go into, like a volcano hole, a deep one. It's rolling along, it doesn't go down in the deep hole, because if it starts to climb the hill and then rolls away again. But if you made it go fast enough, it'll fall into the hole. And so if you have something like wood in oxygen, there's carbon in the wood from a tree, and the oxygen comes and hits it, carbon, but not hard enough. It just goes away again. The air is always coming, nothing's happening. If you can get it faster by heating it up somehow, somewhere, somehow, get it started, a few of them come fast. They go over the top, so to speak. They come close enough to the carbon and snap in. And that gives a lot of jiggly motion, which might hit some other atoms, making those go faster so they can climb up and bump against other carbon atoms, and they jiggle, and they make others jiggle, and you get a terrible catastrophe, which is one after the other. All these things are going faster and faster and snapping in, and the whole thing is changing. That catastrophe is a fire. It's just a way of looking at it, and these things are happening. They perpetual, once it gets started, it keeps on going. The heat makes the other atoms capable of reaching to make more heat, to make other atoms, and so on. So this terrible snapping is producing a lot of jiggling. And if I put, with all that activity of the atoms there, and I put a cup of coffee over that mess of wood that's doing this, it's going to get a lot of jiggling. So that's what the heat of the fire is. And then, of course, if you see, this is what happens when you start to think. You just go on and on. Wonder where, how did it get started? Why is it that the wood's been sitting around all this time with the oxygen all this time, and it didn't do this earlier or something? Where did I get this from? Well, it came from a tree. And the substance of a tree is carbon. And where did that come from? That comes from the air. It's carbon dioxide from the air. People look at trees and they think it comes out of the ground. That plants grow out of the ground. But if you ask where the substance comes from, you find out, where do they come from? The trees come out of the air? They surely come out of the air. No, they come out of the air. The carbon dioxide in the air goes into the tree, and it changes it, kicking out the oxygen and pushing the oxygen away from the carbon and leaving the carbon substance with water. Water comes out of the ground, you see. Only how did it get in there? It came out of the air, didn't it? It came down from the sky. So in fact, most of a tree, almost all of the tree is out of the ground. I'm sorry, it's out of the air. There's a little bit from the ground, some minerals and so forth. Now, of course, I told you the oxygen, we know the oxygen and carbon stick together very tight. How is it the tree is so smart as to manage to take the carbon dioxide, which is the carbon and oxygen nicely combined, and undo that so easy? Ah, life. Life has some mysterious force. No, the sun is shining. And it's the sunlight that comes down and knocks this oxygen away from the carbon. So it takes sunlight to get the plant to work. And so the sun all the time is doing the work of separating the oxygen away from the carbon. The oxygen is some kind of terrible byproduct, which it spits back into the air, and leaving the carbon and water and stuff to make the substance of the tree. Then when we take the substance of the tree and stick it in the fireplace, and there's all the oxygen made by these trees, and all the carbon would much prefer to be close together again. And once you let the heat to get it started, it continues and makes an awful lot of activity while it's going back together again. And all this nice light and everything comes out, and everything is being undone. You're going back from carbon and oxygen back to carbon dioxide. And the light and heat that's coming out, that's the light and heat of the sun that went in. So it's sort of stored sun that's coming out when you burn it, a log. Next question, how is it the sun is so jiggly, so hot? I gotta stop somewhere. I'll leave you something.